Hello everyone. This is the continuation video on solid state and this is solid state part 19. And in this video, I'm going to talk about the structure of a diamond. In fact, it is going to be a very short video and let us study the structure of diamond in this particular video. So here you might have studied the structure of diamond. So diamond is an allotrope of carbon and it is made up of carbon atoms, and carbon atoms are sp3 hybridized and every carbon atom is attached to four other carbon atoms. So all those things you might have studied in some other chapter, but here we have to study the structure of a diamond. Here, what is the coordination number, what is the packing efficiency, and what is the mass of one unit cell. These are the parameters we are going to study. And here, structure of diamond. So not only diamond, any compound which is having the structure related to diamond, all those compounds are said to be diamond cubic solids. Those solids are said to be diamond cubic solids. So solids which follow the structure of diamond are said to be diamond cubic. Basically, diamond has cubic structure. And one important point, that is location of carbon atoms. Very clear, diamond is a crystalline allotrope of carbon and it is made up of carbons. And what is the location of carbons? And the most important thing here in diamond, carbons, carbons are present at the face centers, corners, and 50% of tetrahedral voids. That means carbons form FCC lattice and some other carbons occupy 50% of tetrahedral voids. 50% of tetrahedral voids. That means carbons are at three places: face centers, corners, and 50% of tetrahedral voids. And based on this information, if you calculate a effective rank of this unit cell, Z effective, so face centers are 6, contribution is 1 by 2, corners are 8, contribution is 1 by 8, and totally there are 8 tetrahedral voids. 50% of tetrahedral voids are occupied, so that is 1 by 2 into 8. So this is 6 into 1 by 2 3, 8 into 1 by 8 1, and 8 into 1 by 2 4. So altogether each unit cell of diamond has effectively 8 carbon atoms. Effectively 8 carbon atoms. Somehow it is related to zinc blende structure. If you can recollect, in case of zinc blende, FCC lattice is formed by sulfide ions and Zn plus 2 ions occupy 50% of tetrahedral voids. But what is the difference between this diamond and zinc sulfide? The only difference here, all are carbon atoms, but their sulfide ions are forming the lattice and Zn plus 2 ions occupy 50% of tetrahedral voids. And here Z effective is 8. And the coordination number, if you observe, very clear. Here carbon, some carbon atoms are occupying 50% of tetrahedral voids. So carbon is sitting in tetrahedral void. You already know tetrahedral void is surrounded by 4 particles or 4 spheres, hence the coordination number is 4. And even some carbons are present at face centers, some carbons are present at corners, some carbons are present at 50% of tetrahedral voids, whatever it may be the carbon. So every carbon is surrounded by 4 other carbon atoms. Nearest neighbors, number of nearest neighbors is 4, and here coordination number is 4. And the most important thing here, we need to find a Z effective. Based on Z effective, we have to find a packing efficiency or packing fraction. See, this is the arrangement of carbon atoms on body diagonal. See, for example, this is one carbon atom present at the corner, and this is carbon atom present in tetrahedral void. And tetrahedral void, you know, that is lying on body diagonal at 1/4 distance from the corner, right? So here, if you see the distance between the nuclei of these two carbon atoms, center to center distance. So here nucleus of this carbon, nucleus of this carbon, if you see the distance between the nuclei of these two carbons, that is 1/4 of body diagonal. Body diagonal is root 3a. 1/4 of body diagonal, root 3a by 4. And here this is carbon, this is also carbon. So this is radius of carbon, this is radius of carbon. So that is 2r, where r is radius of carbon. 2r is equal to root 3 times of a by 4. This is a radius of carbon. And finally, we need to find the packing efficiency of the diamond. Packing fraction, packing efficiency. So packing fraction, if you calculate, totally there are 8 carbon atoms, volume of 8 carbon atoms by volume of unit cell. So 8 carbon atoms. Each carbon atom volume is 4 by 3 pi r cube. So 8 carbon atoms, 8 into 4 by 3 pi r cube. So this is the volume of all carbon atoms present in diamond unit cell. And cubic unit cell volume is always a cube. And packing efficiency is equal to packing fraction into 100. And from this we can find A. From this we can find A value. A is equal to 8r by root 3, but we need a cube, so that a cube is equal to 8 cube r cube by root 3 cube, that is 3 root 3. So here that is ultimately what happened, this is 8r by root 3 whole cube, 8 cube r cube by 3 root 3. And if you simplify, you will be getting that is 34%. Packing efficiency is 34% and packing fraction is 0.34. When compared to zinc sulfide, zinc blend, the packing efficiency is very less. Packing efficiency is very less, that is 34%. And what are the other examples which are having diamond-like structure? Germanium, silicon, gratin, these elements also crystallize in the same way as diamond. So this is about the structure of diamond. And one more important point here, there are 8 carbon atoms effectively, and the mass of each unit cell, if you take atomic mass of carbon is 12, 12 into 8, that is 96 AMU. So the mass of one unit cell, the mass of one unit cell of diamond, if you take, that is 8 into 12 AMU. So this is about the structure of diamond. And this is the end of this video. Thank you very much.